Hi everyone, so good evening and welcome to my class. This session is going to be on Fourier series and this is kind of farewell to Fourier series. Okay, so we will be starting Fourier transform from next session, and once the Fourier transform will be finished, we will start communication system as well, right? So this session is going to be a very informative session, so you have to watch from very beginning to the end, right? And you will be learning many concepts. So in this session, I'm just going to talk about convergence rate. Okay. So basically, you know that Fourier series is used for what, right? Suppose we have got any sort of square pulse or triangular pulse. Okay. So we try to find the Fourier series, okay, for any periodic signal, and what we see over there is we try to convert any non-sinusoidal signal to a sinusoidal signal, right? Okay. Understand. So any non-sinusoidal in the sense that triangular or sawtooth waveform or trapezoidal, or let's say any other, okay, where the discontinuities are present, jump discontinuity, okay. So we try to convert them into, different harmonics, okay, right? So in this session, I will be talking about convergence rate. Okay, the convergence rate. What is the meaning of convergence rate? Okay, convergence rate. And this is your final session on Fourier series, right? So convergence rate, like, see, we have computed the Fourier series coefficient for periodic signal. And we have also seen that the Fourier series coefficient, if I talk about Ck, that it varies according to 1 by k, right? Okay. So these are the k means the k is here the integer, and there will be k harmonics. Okay, so ck always decay, ck always decay with harmonics index k, right? Okay, or you can say that ck in general, if I talk about ck, basically decay with this formula. You can say ck is proportional to 1 by k to the power n. Now the question is, what is going to be this n, right? See, as the number of, as k increases, your ck will what? Your ck will, if it is increasing, means ck is gonna decrease, right? Okay, your Fourier series coefficient, the magnitude is going to be decreasing as k increases, right? Now we need to find out, this is in general, right? This is in general, right? This is in general. Okay, so you will find that whenever you compute the Fourier series coefficients, you will find this k always sits in the denominator, right? So ck is proportional to 1 by k to the power n, right? So the Fourier series coefficient ck of the periodic signal, and ck is nothing but exponential Fourier series, usually decay with the harmonic index k. So k is here the harmonic index as 1 by k to the power n. So suppose n is large, okay, so larger n, what does this larger n implies? The larger n implies the faster convergence, you can say faster convergence. Okay, larger n implies the faster convergence. Okay, and there will be what, you have to keep in mind, if n is very small, right? If n is going to be very small, then what problem will be there? The convergence will not be faster. Okay, it will be slower. Okay, and there will be, you can say very fewer term in the truncated series. Okay, will be there, and the signal is going to be smoother as well, right? So see, so how do we compute this n? That is the question. How do we compute this n? How can you say that ck is proportional to 1 by 1 by k, or you can say ck is proportional to 1 by k to the power 2, k to the power 3, and so on and so forth, right? So there is a concept, right? Please remember. So larger k, larger n implies what? Faster convergence. Okay. So we can establish n. Okay, we can find n value, or we can establish n without computing the Fourier series coefficient. This is very important. Okay, remember, we can establish n without computing ck. Okay, without computing ck, you can find out you can establish n. Okay, how, what is the which property we are going to use? So we can use the differentiation property or derivative property. So using derivative property of the Fourier series. If you know the derivative property of the Fourier series, when we differentiate our time domain function, or you can say any periodic signal, so what we can get at the end of the day, we might get the impulse, right? Okay, suppose we have got impulse only, so you don't have to differentiate that, because the coefficient will be independent of k. Okay, if there is a impulse train, right? So coefficient is going to be independent of this harmonics k. Okay, ck is just is equal to what, 1 by t, or 1 by the time period, right? But suppose we have some other kind of signal, periodic signal, like square pulse, sawtooth waveforms, trapezoidal, okay, trapezoidal waveforms. So my ck is going to be dependent on k as well, right? So ck will be proportional to 1 by k, 1 by k square, 1 by k to the power n in general, right? So we can find this n, or we can find this we can establish n without computing ck. That is the beauty of derivative property. Okay, that is very important to keep in mind. Okay, so the convergence rate indicates what does convergence rate indicates? It basically indicates what, how rapidly the reconstruction approaches to the original signal, right? Okay, so suppose you have got any non-sinusoidal signal, and you're going to find the Fourier series. So you will get what, the sinusoidal. Okay, so while reconstruction, right, it should approach to the original signal, right? That is what the convergence rate meaning here is. Okay, so uh, so how do we find out this? And we can find out by finding the by applying the Fourier that derivative property. Okay, understand? So suppose we have got the coefficient, like suppose we are talking about impulse train. Okay, so in case of impulse train, right, the coefficient Fourier series coefficient here is independent of k, right? So you don't have to worry about n or something, right? It will be independence, right? It does not have any sort of dependence on k. And if Fourier series or you can say if periodic signal is differentiated n times, okay, so other than the impulse, okay, if you will be given any sort of waveform, it can be half rectified waveform, or full rectified waveform, or you can say uh, sawtooth waveform, triangular waveform, okay, any sort of waveform. Your Fourier series coefficient is going to be dependent on k, right? That is very important. So what you have to do, you have to differentiate what, you have to differentiate the periodic waveform. Okay, and you have to differentiate how many times, that is a question. Okay, so differentiate your periodic signal xpt how many times? N times. Why n times we are differentiating? So that we can get the first impulse, right? So you have to differentiate n times before it shows first impulse, right? Before it shows the impulse. Okay, so this n is going to be the value, okay, that ck is going to be proportional to 1 by k to the power n, right? So how many times you are differentiating a signal or waveform so that you will be getting an impulse? Okay, that is the idea behind finding this n. Okay, so remember, this is important concept. Okay, because as soon as the impulse come, your coefficient is going to be independent, right? Okay, okay, so your xk is, sorry, your ck is going to be proportional to, right, your ck is going to be proportional to what, 1 by j k omega naught to the power n, right? Understand? from the, from what, from the you can say from the derivative property, this term is going to be will be present, okay, in the ck. Okay. So now you see here your ck is proportional to 1 by k to the power n from here, right? If you just ignore j and omega naught, right? So thus your ck decay as 1 by k to the power n. Understood? So the measure of smoothness, okay, may be described by what? How many times the derivative you are doing, okay? How many times you are differentiating a waveform, okay, to the first impulse, okay? As soon as you start getting the impulse, you stop. Don't differentiate further, okay? That is the idea here. Suppose you have got trapezoidal or half wave sinusoids or half rectified sinusoids. Suppose you have got trapezoidal, and you can say that half rectified waveform. Now think about how many times you will differentiate these waveforms so that you can start getting the impulse. So you need to differentiate 2 times, okay? You need 2 times differentiation, or you can say you need 2 derivatives, okay, 2 times differentiation before you will start getting the impulse. So your ck is going to be the convergence rate, you can say. In this case, the ck will be proportional to 1 by k square. Understand? 1 by k square. Understood? And if I talk about sawtooth waveform or square waves, right? Sawtooth waveform or square waves, sawtooth and the square waves, okay. So how many times you have to differentiate square waves? Square wave, if you differentiate 1 time only, right, you will start getting the impulse, okay? The moment you differentiate 1 time, you will start getting the impulse, okay? So only 1 derivative is required, right? 1 time differentiation, so it will represent ck will be proportional to 1 by k, okay? Sawtooth waveform look, the square waveform look like this kind of a square waveform, okay? So if you differentiate this, you will start getting the impulse. And I hope everybody knows how to differentiate a signal. I have told you in the basics, okay? So please do remember that, okay? So this is one of the important concepts that I wanted to highlight. So convergence rate, what it means and how do we find out, okay? So this is the conclusion. So the convergence rate indicates how rapidly the reconstruction approaches to the original signal, right? And the convergence rate is 1 by k to the power n if n derivatives are required for impulse to first appear. Okay. Larger n matlab faster rate means smoother signal. Okay, your signal is gonna be smoother, and signal with jump shows poor ignorance convergence, sorry. Okay, मान लो तुम्हारे पास इस तरह का है, so it will show poor convergence, okay? ck is gonna be proportional to 1 by k only. This is poor convergence, okay? So I will take one question, right, and we will try to solve that question. That question was asked in GATE 2014, okay, in set 2 paper. So I will take that question and try to solve that. ठीक है, देखो क्या question था. So question was this, right? You see this question. So consider the periodic waveform, okay, in the figure shown. So what you have been given a periodic waveform, which is nothing but a square waveform only, right? The ratio of the power in 7th harmonic, okay, these are the k equal to 7 and k equal to 5 they have given, right? So these are the harmonic index, you can say. Harmonic index. Okay. So the ratio of power in the 7th harmonic to the power in the 5th harmonic for this waveform is closest in the value 2, right? So you have to find the ratio here, right? And that to power. So you know that if you know the coefficient, right? So what is the relation, guys? What is the relation between if you know the coefficient, right? So you can find out the power by using the Parseval relation. So by Parseval relation, right? Parseval's, what Parseval says that over the period, over the period, you can say that the power in the time domain will be equal to the if you take the coefficient, square it, okay, and try to compute the power, right? So that is going to be the partial relation, right? So see, this is going to be a total power, right? Total power. So if you have been given a coefficient, you can find out the power that I have told you. So before finding the power, you need to square the coefficient, right? So here they have given us, what they have given here is they have given the seventh harmonics as well as the fifth harmonic. So in case of exponential Fourier series, we need to consider c minus 7 and c7. Both are going to be same, right? And c5 and c of minus 5, right? Understand? So what we have to do now is we can add square and add them, right? And take the ratio. Okay. So we know that this is nothing but your square waveform. So the convergence for this waveform is going to be what? Ck is going to be proportional to 1 by k. I hope this makes sense. So your c7 is going to be proportional to 1 by 7, right? I hope this makes sense. Okay. Or you can say that your c5 is proportional to 1 by 5 only. Okay. Yes. So the ratio of the power ratio, okay, is going to be what? So you need to take the you can say c7 square plus c minus 7 square upon, okay, 7th square upon 5, yeah, and this is c5 square plus c minus 5 square. Okay, other harmonics we don't have to consider, they have just asked. Okay, so this is how we have to approach it. Now you know that both are same. You can say that this is going to be 2 times c7 square by 2 times c5 square, and this is cancelled, right? Now the ratio becomes what? Ratio is going to be 1 by 7 whole square by 1 by 5 whole square. So this is nothing but 25 by 49, right? 25 by 49. So answer is very simple now, right? So 25 by 49 is what? Let me use the calculator as well. Scientific calculator. 25 by 49. 25 by 49, which gives 0.5 nearly, right? Yes. So let me also verify the answer for this question. This question was asked in 2000, and 19, 1 minute. Yeah, 0.51. So the answer for this question is 0.51, right? According to the scientific calculator as well. And they have given the range from 0.50 to 0.52. So I hope this makes sense. This is very simple question. If you know the convergence rate, okay, and the given waveform is nothing but the square waveform. So your ck will vary, your ck will decay according to 1 by k. ठीक है, जहां n की वैल्यू क्या है 1 है केवल, तो आप इसका आंसर आराम से बता सकते हैं. ठीक है. So this question was very simple and you just need a concept, right? Okay. Now we will talk about next concept that is called as Gibbs of effect, right? The Gibbs effect. The Gibbs effect, okay? See, first of all, let me tell you guys, the Gibbs effect will be present, okay, whenever the waveform will be having a jump. Okay, if the waveform does not have a jump, right, so there will not be any sort of you can say the Gibbs effect kind of thing, right? So if this is important concept, okay, so Gibbs phenomena means what? The if there is a jump, so there will be a effect, okay, and if there is no jump, right, so there will not be any gives effect, okay. Now, so we need to understand that, as I said to you, ki uh, the convergence rate, right? So the convergence rate is one of the important thing, right? So suppose we have got a signal of this kind, right? There is a jump, okay, so we'll try to approximate this signal to the sinusoidal, okay. So while finding the sinus like approximating this, or while reconstructing the sinusoidal signal, okay, since there is a, you can see here there is a jump, right? Okay, there is a jump, okay. So it will be very difficult to reconstruct the signal, okay. The reconstruction is going to be very slow, convergence rate is going to be very slow in this case, okay. So in that process there will be imperfect reconstructions, okay, and there will be overshoot as well, okay, at the jump. यहाँ पर overshoot रहेगा, कुछ ऐसा overshoot आ जाएगा, overshoot will be present, okay. Understand? So the Gibbs phenomena will be present here, ठीक है. So I'm just going to summarize here, okay, and you just keep in mind these 2-3 points related to Gibbs effect, okay. That's it. So Gibbs effect is what it is, nothing but a what perfect reconstruction is impossible for signal with jumps, okay. So अगर कोई भी signal waveform दिया है, कोई भी waveform दिया है, periodic waveform, and if it has some sort of a jump, so perfect reconstruction will not be possible, okay. And reconstructed signal shows overshoot and undershoot, okay, and about 9% of the jump near the each jump location, 9% of the jump, okay. Please remember the the Gibbs effect is present for the signal with jump, right? And your ck will be this is ck only, right? Please remember this is ck, okay. So we can write ck decay as 1 by k, or you can say slower. And if there is no Gibbs effect, like you can say trapezoidal or sinusoidal, okay, so there will be no Gibbs effect because there is no jump, right? So for the signal with no jump, so ck will decay like this. That's what you have to just keep in mind, okay. And okay, related to this Gibbs phenomena, okay. Yeah, so I'm just going to show you some waveforms so that you can understand, right? So you see here, I'm just going to bring this waveform here. Yes. So this is nothing but a sawtooth waveform, okay. Sawtooth waveform, and the time period is 2, and the harmonic index here we have taken k equal to 21, right? So you see here, guys, we are trying to reconstruct this. So there is a ripple, okay, there is a ripple, and here also we are having some ripple, but at the jump, okay, there will be some sort of overshoot, and there is a some sort of you know, undershoot is there, okay, okay, at this jump location you see always, right? So Gibbs effect has to be seen at the jump location only, right? If there is no jump, ओके सो देखो यहाँ पर ये क्या रहेगा, स्पाइक टाइप का रहेगा कुछ ऐसा. देख यहाँ पर भी देख सकते हो कि देयर इज अ स्पाइक. सपोज वी आर इंक्रीजिंग द हार्मोनिक इंडेक्स k equal to 51, so it is trying to okay, there is again overshoot and there is undershoot, right? Now we are trying to reconstruct the actual sawtooth waveform. So here you see there is a overshoot and there is a undershoot, right? Okay. So this is the illustration illustrating the Gibbs effect for sawtooth waveform, right, or sawtooth signal, okay. So you will be given coefficients, okay, and you can say related to sawtooth waveform, and you have to reconstruct the signal back, okay, from the coefficient, Fourier series coefficients, okay. So these things can be seen in the function generator, but we don't have the function generator. We have to just understand the concept कि ये जो overshoot है and undershoot है, that will be present at the jump location, okay, and you know 9%, okay, 9% of each jump, you can say, right? about 9% will be there. Reconstructed signal shows overshoot and undershoot, okay, about 9% of the jump. Okay, there is a, you can say 100% jump, right? There is a complete jump, but 9% will be the overshoot and the undershoot, okay, near each jump location. And each jump location, the reconstructed value equals to the midpoint value of the jump. ये भी पॉइंट आपको याद रखना है, ये वाला. So this is the first point, second, third, and fourth. So at each jump location, the reconstructed value equals the midpoint value of the jump. Okay, midpoint value of the jump. This midpoint value. Next. So suppose we take one question here. So suppose we have got a question, and you have to tell me the convergence rate. So what is the convergence rate if your CK is going to be, right? What is the convergence rate if CK happens to be what? CK is a complex one, right? So this is nothing but A times A by K plus J B by K square. What is going to be the convergence rate for this? So remember, for large K, B by K square is pretty small, right? Then A by K, okay, so your CK is going to decay according to 1 by K only, not 1 by K square, remember this. So for larger K, okay, for larger K you can say, your CK will vary 1 by K only, right? But for smaller K, right, for small K, okay, for small K, your CK will vary according to 1 by K as well as K square as well, right? Please do remember, okay? So your CK is going to get affected by both terms, okay? CK will be affected by both term, okay? I think this is clear, okay? And if there is a sawtooth waveform, so that is going to exhibit the Gibbs effect, okay? In case of triangular pulse, okay, in case of triangular pulse, suppose there is a triangular pulse, so it will not it will not show any sort of Gibbs phenomena. Please remember that, okay? And let me put one more part, in fact complete statement only, so you guys can go through this, okay? What is that Gibbs phenomena, okay? Yes. So this you can go through, okay? The convergence rate is tied to reconstruction from a finite number of harmonics. The faster the rate at which the coefficient decay, the less impact the higher harmonics have on the reconstruction. For signal with jump, okay, the harmonic decay as 1 by K, and we observe some remarkable anomalies, right? The oscillation and the overshoot persist near the discontinuities, but become compressed their as their frequency increases, as capital N is increased, right? The peak overshoot moves closer to the discontinuities, okay, as N tending to infinity, the overshoot narrows, okay, into spikes, but its magnitude remain constant at about 9% of the magnitude of the discontinuity, right? Suppose this is a magnitude of discontinuity, so 9% will be persisting over there, right? ठीक है, तो ये चीज आप रीड कर लेना, okay? And just remember, if there is a jump, okay, if there is a jump signal with jump, so there will be a Gibbs effect. If there is no jump, there will not be any sort of Gibbs effect, right? So please go through that and you will be able to just get the information. 3-4 points are important, that's it, okay? Fine. So now we will talk about system response to periodic inputs. That is important. System response to periodic input. ओके, सिस्टम रेस्पॉन्स टू पीरियोडिक इनपुट, ये इंपॉर्टेंट आपके लिए है, ठीक है, क्योंकि इनपुट में पीरियोडिक सिग्नल दिया रहेगा एंड यू हैव टू फाइंड द सिस्टम रेस्पॉन्स, राइट. सो व्हाट यू कैन डू हियर इज यू कैन फाइंड आउट द फोरियर सीरीज कोएफिशिएंट एंड देन you will get the answer, right? So the Fourier series basically allows us to evaluate the steady state response of LTI system. Remember, whenever any input is given that is periodic input, okay, and you're trying to find the output, okay, of the LTI system, that is called as steady state response. क्या बोलते हैं उसको? स्टडी स्टेट रिस्पॉन्स बोलते हैं. ये हर साल एक क्वेश्चन इंपॉर्टेंट है, आता ही आता है, स्टडी स्टेट रिस्पॉन्स, ओके, ऑफ LTI सिस्टम. इनफैक्ट मैंने बेसिक्स में भी कवर किया है, ठीक है. सो we have already seen, right, if you give you can say that complex sinusoid to the LTI system like this. मान लो तुम्हारे पास एक LTI system है, this is LTI system, and if you're giving input as e raised to power j k omega naught t, right, so what is the output here? The output is also going to be e raised to power j k omega naught t, but there will be one more, okay. So this is called as what? This is basically called as eigen function, right, and there will be an eigenvalue which is nothing but h j omega k omega naught, right. Okay, so you have to find the impulse response, okay, you have to find the frequency response, okay, that is nothing but h k omega naught, okay. So the response of LTI system to harmonic e raised to power j k omega naught t is also a harmonic only, but there will be one you have to multiply the eigenvalue which is h k omega naught, okay, at the input frequency, okay. So you have to find the magnitude as well as the phase, and that is determined by the system h omega, right. So this LTI system will be having a frequency response that is h omega, right. So omega has to be replaced by the input frequency, so you have to evaluate at omega equal to k times omega naught, okay, so that you can find out the magnitude as well as the phase, okay. Okay, so that is very important, okay. So this we have already seen, okay. So देखो, the structure you have to remember. Suppose this is nothing but the impulse response as frequency response, and input is given as j k omega naught t. So what is the output, guys? Output is going to be h, okay. You have to just replace this omega, right, replace this omega by k omega naught, okay, e raised to power j k omega naught t, and let's say that this h k omega naught has got the amplitude or magnitude hk and angle phi k. And how to find out hk and phi k? That at the input frequency only, and this is a property, if input has omega naught, so output must also have the omega naught, same frequency should be there, right. So this can be written as e raised to power j k omega naught t if you are giving input, so it will give you the output as hk, that is magnitude, times e raised to power j k omega naught t, okay, plus phase will be added here, ठीक है. So अगर आप यहाँ पर कोसाइन साइनोसाइडल देते हैं, suppose this is nothing but h omega, and this is you are giving at sine you can say that sine k omega naught t, so output will be what? Output is gonna be the magnitude evaluated at k omega naught sine k omega naught t plus phi k, the angle, okay, angle as well as the magnitude will be okay. So the input is going to get multiplied by the magnitude evaluated at input frequency as well as the phase will be added, right. अगर कोसाइन है यहाँ पर है कोसाइन k omega naught t, so output is also going to be cosine k omega naught t plus phi k phase, and this is the magnitude or amplitude you can say, ठीक है. which is evaluated at input frequency, and this is the property of LTI system, right? So this is also known as steady state response. इसको क्या बोलते हैं? Steady state response. Steady state response. हर साल एक क्वेश्चन आता है, ठीक है? Each year you will find one question. So we multiply input magnitude by HK, and okay, that is very important. Okay, and you have to also add the phase. Adding the phase means you are augmenting the phase. Okay, you are increasing the phase by. Fine. So I hope this makes sense to all, right? So suppose you have got any input, you can say, which is a periodic signal. So first of all, you can find out the Fourier series, right? And then you can find out the response. Okay. So suppose we have got the input as 1 minute. Suppose we have got the input as CK. Okay. CK cosine Q omega naught T plus theta K. Okay, this is the input, and we are applying to the LTI system. Okay, this is nothing but your LTI system having the frequency response H omega. So your output is going to be CK HK, right, cosine Q omega naught T plus theta K plus phi K. Everything is going to be same, right? Input phase and everything, but some extra phase will be there, and some extra you can say multiplier will be there, that is magnitude. Okay, that can be computed using okay, that is very important to keep in mind. Okay, so we have to evaluate the magnitude, okay, of the frequency response at input frequency only. That is very important. Okay, now suppose we are giving input as suppose we are giving input, this is LTI system. Okay, and it has the impulse response H omega, and we are giving input as what? K is going from minus infinity to infinity, Ck e raised to power jk omega naught t, which is nothing but xt. This is the exponential Fourier series. Okay. So what is going to be the output? So output is going to be by t will be equal to, you know, Ck e raised to power jk omega naught t will be present over there, right? But you have to, so it will be nothing but output is going to be summation minus infinity to infinity Ck, but remember the magnitude H q omega naught, okay, e raised to power j q omega naught t plus phi k, right? Okay, so you have to multiply this guy, okay, to each term of the Fourier series. Each term of the Fourier series you have to multiply by the magnitude of the frequency response, and you have to add the phase, extra phase. So extra thing I am highlighting here. ठीक है, बस इतना ही आप अगर आपको पता है तो you can find out, you can solve any question. ठीक है. So I think this is clear, and once you will learn the Fourier transform, so you will be able to find out the frequency response very easily. Like we have to find the Fourier series only, right? I mean Fourier transform. So this is how things get over. बस एक concept और बचा है, that is known as Dirichlet condition, right? Okay, we call it Dirichlet condition. So I will just discuss that. ठीक है. Now we will talk about Dirichlet condition. Dirichlet condition. What is the meaning of that? So in case of Dirichlet condition, you have to make sure that your signal is absolutely integrable. Okay, signal must be absolutely integrable. Okay. So Dirichlet condition describes sufficient condition for existence of Fourier series. Okay, suppose given a waveform, whether the Fourier series will exist or not. राइट. दिस कंडीशन इज गोइंग टू एंश्योर. ठीक है, तो क्या क्या कंडीशंस हैं बस आपको उतना ही जानना है. तो Dirichlet condition describes sufficient condition for existence of Fourier series, and the periodic function xt will have a unique Fourier series if over one period only you have to check, right? Over one period. Okay. Over one period, if xt is absolutely integrable and if xt has finite number of maxima and minima and finite number of finite discontinuity. Okay. This is known as Dirichlet condition, right? And it is sufficient condition for existence of Fourier series. ठीक है, okay, that is very important to keep in mind. क्योंकि आपको पता है कि we have got the signal, okay, which are non-sinusoidal signal, they have discontinuity. But if there is a finite number of finite discontinuity, there should not be infinite discontinuity, right? That is also very important. ठीक है. So let me take some example where Fourier series does not exist. Suppose number one is xt is given as, I'm going to focus on single one period only. So xt is nothing but you can say that sine 2 pi by t, okay, over 0 to 1, right? Or you can say that xt is given as cosine 10 pi t, okay, and again this is nothing but 0 to 1, okay. So they have infinite number of maxima and minima. Remember, they have infinite number of maxima and minima, therefore Fourier series will not exist. Okay, so you have to ensure that xt must be absolutely integrable and xt has finite number of maxima and minima and finite number of finite discontinuity over one period. ठीक है, अंडरस्टूड. अब मान लो तुम्हारे पास ऐसा दिया है कि सपोज xt इक्वल टू 10 t, okay, and t over one period, so 0 pi by 2, so it will be having infinite discontinuity, guys. Infinite discontinuity, right? Infinite discontinuity, okay, per period. ठीक है. So I hope this makes sense. So if there is an infinite number of finite discontinuity, okay, so it will not be having what the Fourier series, right? So ये आपको याद रखना है बस. ठीक है. So yeah, so Dirichlet conditions are satisfied by most of the periodic signals. Dirichlet conditions over one period. Remember, over one period. You have to always check over one period. A periodic signal xt must be absolutely integrable and contains a finite number of maxima and minima and finite number of finite discontinuity. बस खत्म. इतना ही जानना है, ज़्यादा नहीं जानना है. ठीक है. Just understand these conditions, okay. Why we are studying these conditions? Just to for the sake of existence of Fourier series. ठीक है, बस बाकी आपको क्वेश्चन प्रीवियस ईयर करने हैं एंड दैट्स इट. ठीक है. सो this is one important concept that I wanted to highlight. ठीक है. So existence is very important. So over the one period, that should be absolutely integrable. Absolutely integrable means that must be less than you can say xt, sorry, less than infinite. ठीक है. And convergence also is very important. Convergence means what? Suppose you have got actual signal xt and जो आप reconstruction कर रहे हो, that is nothing but up to certain harmonics. ठीक है. And try to find the difference and then try to find the you can say that energy, right? And if n increases to infinity, like number of you can say harmonics you are increasing to infinity, or ठीक है, देखो, suppose over the period xt square is less than infinity, this is first condition, ठीक है. So if signal is absolutely integrable over one period, so it also includes the it can be the energy signal, right? Okay. And every continuous and piecewise continuous signal over one period must be what? Square integrable, ठीक है. So Fourier series also converges to xt, ठीक है. तो देखो, मान लो तुम्हारे पास एक xt है एंड एक रिकंस्ट्रक्टेड सिग्नल एक्स एन टी है. दोनों के बीच में डिफरेंस निकालने का मतलब क्या है? एरर. उसका एनर्जी निकालिए ओवर, ठीक है, ओवर वन पीरियड, एंड दैट शुड लीड टू जीरो, ओके, एज एन लीड टू इंफिनिटी. सो दिस इज नथिंग बट एरर, स्क्वायर एरर, okay, square error, energy of the squared energy of the error signal, you can say, ठीक है. So these are the things that you have to remember. And uniqueness means your power must be, power must not be infinite, the power must be finite, ठीक है. बस इतना ही था फोरियर सीरीज में. एंड आई बिलीव सब लोग क्वेश्चन कर पा रहे होंगे, ठीक है. एंड वी विल नाउ टॉक अबाउट द फोरियर ट्रांसफॉर्म. Fourier transform, and which is kind of prerequisite for, you can say, communication system. Okay, तो अगर आपको continuous time, I will talk about continuous time Fourier transform. There will be discrete time as well, but primarily I'm gonna focus on continuous time, and it is important for communication system. So the moment we will finish Fourier transform, we will go to this, ठीक है. तो Fourier series में कुछ भी नहीं था. अगर हम समराइज करें फोरियर सीरीज, समरी में क्या क्या याद रखना है आपको? एक्सपोनेंशियल फोरियर सीरीज, ट्रिग्नोमेट्रिक फोरियर सीरीज, पोलर फॉर्म, ठीक है. सो उसका सिंथेसिस इक्वेशन याद रखना है, राइट. एंड देन यू हैव टू रिमेंबर द एनालिसिस इक्वेशन, राइट, सबका, इसका 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 इसका, दैट्स इट, ठीक है. एंड देन यू हैव टू रिमेंबर सम ऑफ द इंपॉर्टेंट प्रॉपर्टी, राइट. हाँ, इफेक्ट ऑफ सिमेट्री, ओके, ऑन द एफएस कोएफिशिएंट, ठीक है. फोरियर सीरीज प्रॉपर्टी, ओके, and then convergence rate, डिरिचले कंडीशन, ठीक है. और बस हो गया, ठीक है. और हिडन सिमेट्री का कॉन्सेप्ट जो था, हिडन सिमेट्री, राइट. एंड हाउ डू वी कंप्यूट द फोरियर सीरीज फ्रॉम द गिवन स्पेक्ट्रम. ये सारी चीजें आप देखो बस, बाकी आपको फोरियर सीरीज खत्म है, राइट. सो विल मीट इन द नेक्स्ट सेशन. थैंक यू.